Hi everyone, this is Sheikh Roshan Jamir from CSC department. I am going to explain about the interaction of operating systems and computer architecture, a, work, a workshop summary. Introduction to operating systems. Operating systems, OS, are essential software that manage hardware and provide the platform for applications to run. They ensure efficient resources managing, including memory, processing, and storing. Examples include Windows, Linux, and Mac OS. Introduction to computer architecture. Computer architecture defines how computers' hardware components interact. It includes the design of CPUs, memory systems, and input and output processors. This architecture affects the performance, scalability, and power efficiency of computers. The role of OS in hardware management. Operating systems manage hardware resources by abstracting complex hardware functions and allowing multiple applications to run simultaneously without inter- interfering with each other. This includes CPU scheduling, memory management, and device control. Instruction set architecture ISA and OS. The ISA defines the commands a process can execute. Operating systems interact with the ISA to perform basic tasks such as reading data, executing instructions, and controlling peripherals. Popular ISAs include X86 and ARM. System calls. Bridging OS and hardware. System calls provide the interface between user program and the OS. They allow applications to request services such as file handling, memory allocation, and process management, which are executed at the hardware levels. Memory management and virtualization. The OS handles memory management by allocating space to processes, swapping data between RAM and disk, and using virtual memory to ensure efficient use of resources. Virtualization allows multiple operating systems to share the same hardware resources. It threads. No. Multi-threading and OS scheduling. Multi-threading enables a CPU to handle multiple tasks simultaneously. Operating systems use scheduling algorithms to allocate CPU time efficiently, balancing the workload across different threads and optimizing performance. Input output systems and OS. Operating systems manage input output devices such as keyboards, displays, and storage systems. OS handles device drivers, which translate high level commands into hardware specific operations. Efficient IO management is critical for performance. Cache management in OS and architecture. Cache memory stores frequently accessed data for quick retrieval by the CPU. The OS works with the underlying architecture to manage cache memory, ensuring efficient data access and reducing the time needed for data fetching from main memory. File systems and storage management. The OS is responsible for organizing data into files and directories. It ensures that storage devices like SSDs and hard drives are used efficiently, provides data security, and handles read or write operations through file systems such as NTFS and ext4. The evolution of operating systems. Operating systems have evolved from simple batch processing systems to complex multi-user systems. Key milestones include the development of time-sharing systems, real-time OS, and the rise of mobile OS like Android and iOS. CPU, CPU scheduling algorithms. OS uses various algorithms to schedule CPU usage among processes, such as the first outcome first served (FCFS), shortest job next (SJN), and round robin (RR). These algorithms help ensure that all tasks receive CPU time efficiently. Real-time operations systems (RTOS). RTOS are designed for systems that require real-time processing, such as embedded systems in medical devices and automotive control. They prioritizes tasks to meet the strict timing constraints, ensuring deterministic behavior, power management, and energy efficiency. Modern operating systems collaborate with hardware to reduce power consumption. Features like dynamic voltage scaling and sleep modes help extend battery life in portable devices while reducing energy usage in desktop and servers. Parallel processing and OS support. Parallel processing enables multitasks to be executed simultaneously. The OS must efficiently manage these processes, balancing workloads between CPUs and coordinating inter-processing communication to optimize performance. Virtual machines and hypervisors. Hypervisors allow multiple virtualization machines (VMS) to run on a single physical machine. This is used for servers, consolidation, testing environments, and cloud computing. The OS interacts with the hypervisors to manage hardware resources between VMS. Security mechanisms in OS. Operating systems enforce security through user authentications, access controllers, encryptions, and sandboxing. These mechanisms protect the system from unauthorized access, malware, and data breaches. Kernel modes and user modes. Operating systems operate in two main modes: kernel mode and user mode. Kernel mode grants the OS full control over hardware resources, while user mode limits access, ensuring that applications cannot interfere with system level operations. Process synchronization. Process synchronization. Process synchronization is critical in multitasking environments to prevent race conditions and ensure data consistency. OS provides mechanisms like semaphores and mutexes to control the execution's order of processes. Operating systems for mobile devices. Mobile OS like Android and iOS are optimized for touchscreens, interfaces, and power efficient hardwares. They focus on battery management, mobile security, and app ecosystems to deliver a smooth user experiences. Operating systems. Distributed OS manage uh, multiple computers connected by a network, presenting them as a single coherent systems. This enables resource sharing, load balancing, and tolerance across fault tolerance across distributed environments. Cloud operating systems. Cloud OS provides a platform for running applications and servers in a cloud environment. They manage resources in data centers, ensuring scalability, reliability, and efficiently resource utilization in cloud infrastructure. Networking and operating systems. Operating systems manage network communications by providing protocols like TCP and IP. They control how data is transmitted between devices, ensuring that resources be like bandwidth and connections stability are managed efficiently. Interrupt handling in OS. Interrupts allow hardware devices to signal the CPU when they need attention. The OS manages interrupts by prioritizing them and responding promptly. ensuring smooth execution of critical tasks like I/O processes. OS and GPU management. Graphics process Graphics processing units (GPUs) accelerate computational tasks, especially in graph rendering and machine learning. The OS interacts with GPUs to optimize performance, handle driver supports, and manage multitasking workloads. Open source versus uh, proprietary operating systems. Open source OS like Linux allow users to modify the contribute the software freely. Proprietary OS like Windows and Mac OS are developed by companies, offering closed ecosystems with support, security patches, and regular updates. Cloud native operating systems. Cloud native operating systems are designed specifically for cloud infrastructures, optimizing container orchestration and resource management. Examples include Kubernetes-based systems, which manage containerized applications across distributed environments. Feature trends in operating systems. The feature trends of operating system develops with likely focus on AI integration, security enhancements, and further optimization for multi-core and distributed architectures. OS will also play a key role in development of quantum computing platforms. Conclusion: the interaction between operating systems and computer architecture is critical to maximize system performance, security and efficiency. Continued collaborations between software and hardware development will drive future technologies advancements. Thank you.